All right, this is another packet of notes that I gave you. It actually starts off with an example out of my math lab that someone had asked. So before we get into the notes, let's get this example. It says, assume that the students are separated into a group with IQ scores in the bottom 30% and a second group with IQ scores in the middle 40% and a third with IQ scores in the top 30%. The scores are normally distributed with mean of 100 and standard deviation of 15. Find the IQ scores that separate the three groups. So we don't want the z-scores, we want the actual IQ scores that separate the three groups. So this is what we're looking at. This is the description according to normal distribution. We have our bottom 30%, middle 40%, and top 30%. So we want the z-scores that line up and separate the 30%, 40%, and 30%. So once again, we talked about going inside the chart and finding corresponding z-scores. So we look for, remember the chart that I gave automatically gives you what's to the left of or what's less than. So we look for the closest value to 0.3 inside of your chart. So that'd be 0.3015. So we're talking about 30% is 0.3, 40% is 0.4, and then once again, 30% is 0.3. So we look for the closest value inside of this chart to 0.3, and that is 0.3015. Then the z-score that corresponds to that is going to be negative 0.51. Oh, no, that's 2. Sorry about that. I made a mistake and scratch that out. Negative 0.52. All right. So negative 0.52 separates the lower 30% of your data. Then if you're talking about the upper 30% of your data, remember this is symmetric about the mean. So what you could do is actually go to positive 0.52, which would separate the right 30% or the greater 30% of your data. And if you were to go to the chart, if you look at 0.7, because remember we always talk about the chart give us what's to the left, that means 0.7 would be to the left. If 0.3 is to the right, that means 0.7 would be to the left, and you see the 30% and the 40% will give you 70%. So the 0.7 would be to the left. If you were to go to the chart, the closest value is 0.7. Closest value to 0.7 is 0.6985. So that would be a positive 5.2. So that would match up with the symmetry of your normal distribution. Once again, the data value, that's the z-score that separates the 30%. The lower 30% is negative 0.52. You get that from the chart. And then the z-score that separates the upper 30% will be positive 0.52. Remember, it's symmetric about the mean. All right. So now those are our data values, which represented by X. Those are our z-scores. Remember, the z-score formula is z equal to X minus mu over sigma. In other words, your data value minus your mean over the standard deviation. So now if I decide to solve this relationship or solve this equation or formula for X for the data value, I will end up having mu plus z times sigma. And so I can use that in order to find the data values that correspond to these two z-scores. So we saw that our mean was 100, standard deviation was 15. We established that our first z-score is negative 0.52. Second z-score is positive 0.52. So we plug those values in for each z-score. So in other words, if I want the data value that corresponds to this first z-score, plug in 100, plug in negative 0.52 for that z-score, and plug in 15, that gives me 92.2. And then if I want the second data value that corresponds to the second z-score, plug in 100, plug in the 0.52 and the 15, do your calculation, that's 107.8. So 92.2 will separate the lower 30% of your data, and 107.8 will separate you from the upper 30% of your data. So this next chapter starts off with the correlation coefficient. We start off talking about scatter plots as a primary tool for examining two variable relationships with both variables being numerical, and it will look similar to this. Just your first quadrant and just dots that represent each observation. So when studying scatter plots, we look for trend, which is your center, strength, which represents the spread of data, and then the shape, which is the shape of your data. Your trend We look at first positive associations or positive trends. This is increasing trends from left to right. So if you read your data going from left to right, if it goes up, it's a positive association. Negative associations, they decrease going from left to right, so they go down. When you look at your strength, their weak associations result in large amount of scatter in your scatter plot. Large amount of scatter means that points have a great deal of spread in the vertical direction. Strong associations have little variation, a little vertical variation. The shape, the simplest shape for a trend is linear. Of course, the key word in linear is line. Linear trends are quite common in nature. They are called linear because the trend can be summarized with a straight line. Now, your correlation coefficient is going to be a number that measures the strength of the linear association between two numerical values. So an example of that is the relationship between people's heights and weights. So the correlation coefficient makes sense only if the trend is linear and both variables are numerical. If it's represented by R, it's always between -1 and +1 inclusive. If the value is close to -1 or +1, then the association is very strong. If the value is close to 0, then the association is weak. If the value is positive, then the trend is positive. If the value is negative, then the trend is negative. If R is equal to +1, that means there is a perfect positive linear relation. If it's equal to -1, that means there is a perfect negative linear relation. R being close to 0 does not mean there is no relation, just no linear relation. Here are just examples of what your graph will look like, your scatter plot will look like. If R is equal to 1, it would be a positive straight line. And if it was equal to -1, it would be a negative straight line. Positive association going up from left to right, negative association going down from left to right. And then as you deviate from that straight line, you start to see the spread of your data. So here's an example of how we could use a correlation coefficient. Let's say if we have observation of your heights being 61, 62, 63, 64, 66, and 68, then the corresponding weights being 104, 110, 141, 125, 170, and 160. Says your correlation coefficient will be 0.8809. So this book doesn't focus on the calculation or the using of the formula for the correlation coefficient or the regression line, but it focuses on the application. So what you need to do is find an app, website, or calculator that would use or be able to calculate these two things, the correlation coefficient, which is in 10.1, and the regression line, which is 10.2. And using a reliable app or website, you should get this value of 0.8809. It is positive and it's close to 1, so that makes it a strong positive association. Also, easy website that I've used before, that I told you about before, is easycalculation.com. That one will always work for you. So what it means for 0.8809 to be your correlation coefficient, it says for the height and weights, that means that the taller the person is, the heavier they are. And so if it was negative, that would mean that the taller the person is, the less they will weigh. Let me know if you have any questions.